let's take up another problem, and this problem appeared in IIT JEE 1989. It's an interesting problem. The problem says, in a modified Young's double slit experiment, monochromatic, uniform and parallel beam of light of wavelength 6000 angstrom and intensity 10 divided by pi watt per square meter incident normally on two circular portions A and B of radii 0.001 meter and 0.002 meter respectively. A perfectly transparent film of thickness 2000 angstrom and refractive index 1.5 for the wavelength 6000 angstrom is placed in front of aperture A as it is shown in the figure. Now what we have to calculate the power to be calculated in watt received at the focal spot F of the lens. The lens is symmetrically placed with respect to aperture. Assume that 10% of the power received by each aperture goes in original direction and it is brought to the focal point. Now this is interesting problem, and it is not a straightforward problem. It involves some analysis. Now let us make calculation for intensities at apertures A and B. Now we know that intensity is nothing but energy flowing per second per unit area normally. Now here we are given the value of intensities, that is I1 is equal to I2 is equal to 10 over pi watt per square meter. Now the area of cross section of aperture A, that is A1, will be pi R1 square, and that will be equal to pi multiplied by 0.001 raised to the power 2, and that works out to be pi into 10 to the power minus 6 square meter. Similarly, we can calculate area of cross section of aperture B, that is A2, and it will be pi R2 square is equal to pi into 0.002 square, and that works out to be pi into 4 into 10 to the power minus 6 square meter. Let P1 and P2 be the powers of incident radiation at apertures A and B respectively. Now we know that power is nothing but intensity multiplied by area. So we get the value of P1 as 10 to the power minus 5 watt. Similarly, power P2 will be I2 multiplied by A2, and that gives us 4 into 10 to the power minus 5 watt. Now when we introduce a thin transparent medium in one of the beams, a path difference is introduced. We have already taken up this situation with respect to YDSC, and we know that with the introduction of thin transparent sheet, a path difference of delta x, that is mu minus 1t, is introduced. Now in this case mu is 1.5 and t is 2000 angstrom. So when we make substitution, we get the value of a path difference, and it is 10 to the power minus 7 meter. Now we can calculate the path difference and its equivalent phase difference. Now we know the relationship between phase difference and path difference, and we know that phase difference will be 2 pi over lambda into path difference. So when we make substitution for calculation of phase difference, we get the value of phase difference as pi by 3 radian. Now we know that a resultant intensity at any point as a result of interference of two beams is equal to I1 plus I2 plus twice under root I1 I2 cos phi, where phi is the phase difference between the interfering beams. Now we also know that intensity and power are related by a simple expression, that is intensity is equal to power divided by cross section area, or we can say intensity is directly proportional to power. Now the same relation will be valid for power, and we can write power at the point of interest, which here in this case is the focal point of the lens, will be P1 plus P2 plus twice under root P1 P2 cos phi. We know the value of P1, P2, and also we have calculated power at the focal point, and this value is P is equal to 7 into 10 to the power minus 5 watt. This is the final answer. Now here the point to be appreciated, that the power at the required point will have same relation as it is valid for intensities. So here power will be P1 plus P2 plus twice under root P1 P2 cos phi, a relation which is similar for intensities. That's the only twist in this problem. The rest part of the problem is as usual, and it is a routine part of interference.